Hello friends, it's me again, Dr. Patterson. In this video, I'm going to point out a problem, not only with the simulator, but also with the robotic arms that we have in the physical mechatronics lab. And it mainly goes to that the servos that we use have no speed control, right? You tell them to go to a position and they will try to move there as fast as possible. So let's see what this means for the robot arms. And if you haven't tried this yet, it's entertaining. You should try it. So let's run this. And my favorite part of this is let's go pick up the box. This might take me a second. With how many times I've done it, it should go faster. Nope, nope. Oh no. Oh, yep, I'm just you can see the problem though. Eventually that box will land. Maybe. All right, let me restart this. Nope, it didn't pause. All right, so I picked up the box. Now let's try to move it over. Now you can imagine like having the robotic arm do this. You don't, if it's got something fragile in that box, or the box is literally like maybe a glass vial, you don't want to be whipping it around because one, it could easily break it while it's gripping it and trying to move really quickly, or it could fly out of there. So let's try to place this. And then drop it in there. All right. So now if we wanted to record the different positions that I just moved to, right? Let's say I moved to 6 different main positions and I had those as arrays. I could use each set of positions, the potentiometer readings as the specific locations of which, or for each servo in there. And so I could have for the 5 different servos, 5 different positions that I send it at one point, and then I send it the next thing, and maybe it gets closer to the box, and then I send it another one and it squeezes the gripper, and then I send it another one and it moves up, and then it moves over, and then it moves down and drops it. But if I just send these one at a time to the servos, then that arm is going to do this, right? It's going to go, it's going to just flop around and end up throwing the box. I didn't even think it was possible to throw the box out of the bounds that I made in the software, but apparently it is. So you can see how that would easily be problematic for an actual robot arm. Like in the lab, I've already mentioned, these things end up slamming down into the table, right? And that's because people program it to move from one spot to another and don't provide any speed control. So how could we implement speed control in this? Well, really what we care about is we want to move from one spot to another, and we want to like slowly move to all the intermediate spots in between, right? And so if we wanted to move from, let's say, if this lets me draw, x, let's call it x0, and move to x1, I don't want to tell the servo, let's say right, let's say s dot right position, x0, and then right? If I do that, it's going to move very quickly, no matter what the distance is from the first point to the second point. And so the way that we can do this is by, or slow it down, or set a specific speed that we want to move at, is by breaking this up into segments, right? And what you already have done this in 190, just interpolating between 2 points. So let's start with one servo and test it out. and then we can look at how that'll work for more. So if we wanted to interpolate between those 2 points, well, we could say that the position x, we're starting at x0, right? And so we can say that at time equals 0, we want to start at this first spot. And then as we move to the other one, we'll essentially go from x0 to x1. And so we can say on top of that, we want to add x1 minus x0. And so when we're at the final time of just like t, let's say 3 seconds, at 3 seconds, we're going to be at that final position. And instead of trying to do this, create a function where you have to specify the time or anything like that, we can make it incredibly generic and say this is t equals 0 and this is t equals 1. We're always going to be basing it on when you're at 0, you're at the first point. When you're at 1, you're at the last point. And so there's no worry about the time that we need to put into it. We can use that as one of the inputs into what we're going to create as a function. And so for this one, we can just multiply that difference between those 2 points by that variable t, or that time, 0 to 1 second, for moving from the original spot to the final spot. So what would this look like in code? Let's go back and stop that. And let's go over to my Lerp testing code and just do clear all, close all. And if we were to just create the space that we need to test this out, let's start with an x0 that's equal to 2. And let's have an x1 that's equal to 10. So now we've got 2 points move from one to the next. And we need essentially that variable t to go from 0 to 1. And so we can create the variable t is equal to 0. And then the middle argument for this setup, I can say 0 to 1, right? But really, I want it to increment by 0.1. If I can type. Swear, I don't make this many typos, but when I have this screen right here and my keyboard's off to the side, I make typos all the time. All right, so we've now got a variable t, and if we run this, let's look at what t is. So now we've got a variable t that just increments by 0.1, starting at 0, going to 1. So now we have the start, the end, and then our t variable. And so if we take that function that I wrote out, that simple linear interpolation function, where we have x is equal to x0, forget how, I think I should be able to do this, t times, I forget how MATLAB handles matrix multiplication, if you can do the vector times a scalar. Yes, you can. So what we get out of it is all the points in between, right? And each one of those is scaled by that difference between the two. So the difference is 8. And so essentially that 0.1, every step of the way along there added on to 2. And so we get 2, 2.8, 3.6, 4.4, 5.2. And the cool thing about this function is that we don't need to keep the x, the x0 and the x1 as just a 1D. It's just as a number. We can have it be a vector. We can say, let's start at 2, 2, and go to, let's say 3, 10. So significant difference in one dimension, the first one versus the second one. This might act strangely. Let's find out. Yep. Let's not use dot operator. Let's do it a simpler way than that, because we're not going to pass in, our t variable is not going to be a vector that we pass in. So let's say for t is equal to this. And pass it that, and then type end. And so now we've got that simple function where we're just calculating the current x, or the interpolated value of x. Let's even label that x, say lerp. Lerp is a function, it's one of my favorite functions from programming video games, because you end up using it far more than you think you might. So just linearly interpolating between 2 points, and we're calling it x lerped. So if we run this, we're now going from that original position of 2, 2, and then incrementing each one and finally getting to 310. So if we wanted, let's plot this. Let's say we're going to plot that point. Think of a way that we could save this easily. We can say, let's add an index I out here. Nope, I'm going to start at 1 and say x lerped of I. Nope, not going to like that. But we can say we want it to be each row as we go down. So we can say comma, and then the entire row is equal to that. And so now we have x lerped. And if I wanted to, oh, I didn't increment I yet. I equals I plus 1. Run that. Okay, now we have x lerped in a form where we can plot it. So we could say down here, plot, and we'll use the first column as the x values. So we'll say plot x lerped and pass it for all the rows, first column, and then x lerped for all the rows and second column. We'll plot that. And we get a line that goes from 2, 2 down here up to 3, 10. And so we're going all along there, and we've got a bunch of points. It's kind of probably hard to see these points that are showing up, but each one is one of those data points that we've interpolated between there. So you may or may not be wondering, well, how can we use this as a way to go from one spot to the next, right? Well, this is for a value between 0 and 1. So let's create a function now where we can pass in a t value, or sorry, let's say a start value, an end value, and the variable t, and then output the interpolated value, whether it's 1 dimension or in the case of the robotic arm, 5 dimensions, right? We've got 5 servos to worry about. So let's do a new function, and we can call this one lerp. And the input argument we'll say is start. The second argument is end, and then the last one we'll say is t. And the output argument will be, let's call it the lerped position. And then within this function, we're going to just essentially do the exact same formula that we had. So we're going to, let's delete this. And then the first thing, if we go back here, this will be our, what did I call it? Lerped position is equal to x0 is our start. plus t times, and then we've got the end minus the start. So that's our interpolation function. So let's write that. Our lerp position is equal to start plus t times end minus start. And then save that, and we can save that as, yep, function is called lerp save. And then we can go back to that lerp testing script that I had created. And instead of this function, right, we've got it spelled out there. Instead of that, let's say lerp, and we'll pass it the start, which is x0, and the end, which is x1, and then the t value, which would just be t in this case. And then we can throw a semicolon, and if we plot this, we get an error, invalid use of operator. What the what? Where? Line 1. Oh, in lerp. What did I do? Oh, let's not call it end. Let's call it start position and end position. How about that? Yeah, don't use end. I knew there was going to be something wrong with that. All right, let's try this again. What now? Oops. Getting ahead of myself. Forgot to change out start position. This is what happens when I lecture. Get all excited. It's all the plots. It just blows my mind. So we've got the same functionality now. And we can pass it arrays of any size, and it will go from that start to the end. And it will interpolate along the way. Right now, we use a for loop to just step through specific points, right? And so what could we do? Well, what we can do is say, what if I wanted this to happen over a certain amount of time? So we could say, instead of this, let's say, let's keep the I equals 1 because we want to hold on to the data points. We'll start a timer with tick, and then we'll say, well, talk is less than 5. And within here, or let's even step back a second and say time to move is equal to 5 and replace that. So while talk is less than the time to move, we go into this. And then in here, the t value, instead of sending a specific numerical value, we can say talk, which will give us the current time that's elapsed. And because we know that we want t to be on the range of 0 to 1, we can divide that by the time to move. And so now over a 5-second period, we will move from that one position to the next. So what does that look like? What we can do instead of waiting for that to happen, right? We can cut this plot, and in here, let's put plot. And so it'll update the plot. And then let's pause for 1/10 of a second each time. And so what we're going to see, probably not the greatest thing, is you'll see the line start, and then it will kind of look the same, but you'll notice along the two axes that those values will start to change. So let's run that. And so we can see right now, oh, that was really fast. Okay, let's give myself more than 5 seconds. Let's try time and run it again. All right, so once we pull that over, you can see, like, as the time goes along, we're slowly moving up to that final position of 3:10. And so now we've got like a great way where we can move servos at slower speeds than just saying, this is your absolute next position, right? And so this is kind of the simple way to slow things down is we're telling it to go to all these incremental points in between. And so if we wanted to, it's a good way to do this without giving away the lab. Let's determine 2 specific points for the arm and then have it move back and forth. So let's go over to that lab task from that I put together for the previous week and run it. And what we've got, let's do something like, we'll go from this spot, which we can record somewhere, which I'll record right here. We'll say waist, shoulder, elbow, wrist, and gripper are, that is an E, I promise. In terms of degrees, the waist is 40.5. So we'll say roughly, that'd be, we'll say 0.75, 0.75. The shoulder is -10 degrees. Let's call that 0.45 because just below the halfway point. The elbow is at 25 degrees. So that would be roughly 0.66. And the wrist is right at 0, so that's 0.5. And then the gripper is at 40.59. We'll call that another 0.75. Okay, so we've got our first point. This is our start. And let's say now we want an end. Let's move it over. Like that. Maybe release the gripper and put the wrist down a little bit. And so for the waist, we're at -20 degrees. What would that be? Should just use my calculator. It's cheating. We'll say 0.42. The shoulder is -81. So we'll say 0.05. The elbow is -75. We'll call that 0.15. The wrist is -30. We'll call that 0.35. And then the gripper is at 90, so that's a 1. Okay, so now we have 2 different sets of values, and we're gonna set this up so we can lerp between those 2 different positions with the robot arm. So let's stop that, and let's grab a lot of what I did before and go over to Lerp testing. Our x0 in this case is going to be the first set of values. Let's set up our connection to the MechaGod software first. So we've got our connection here. We've got our potentiometer pins, which we're reading from the software. We've got our servo pins, which will control each servo. And then we've got our start and our end. So for our start, we've got an array that is 0.75, 0.45, 0.66, 0.5, and 0.75. And then for the second one, we've got an array that is 0.42, 0.05, 0.15, 0.35, and 1. And let's say we wanted to move over 5 seconds. So over a course of 5 seconds, we're going to move back and forth. And we're lerping from the start position to the end position with that t value. And so that x lerped row is going to be what we get back from there. And so it's essentially like all those intermediate points between there. Now, instead of plotting, we want to write those to the servos. And so what we can say is first we need to actually create the connections to the servos. Forgot that part. So setting up each servo in the array, and then we need to write that each one of those positions. And so in the while loop, we want to say, instead of plot, we'll comment that out. We're going to say for j is equal to 1 to 5, and end, we will, for the servos, ms.write position, and we'll pass it each one of the interpolated values. So this would be x lerped, and it'll be index I, comma j. And we want to make sure we're addressing the right servo here. So we got to go back and say, in this case, it would be servo j, and the jth element in that row would be the position that we want to send it. Think it's going to work? I know I've made a lot of typos and mistakes so far. Let's give it a try. Nope. Index in position 1 exceeds array bounds. Oh, can't change I until after I'm done with that number. And so now we have not the exact positions, but we have it lerping between two spots. So what could we do if we wanted it to go back? We could say for I, let's say we wanted to go back and forth 5 times. For, oh God, we need another index. K is equal to 1 to, let's say, 10 times. We'll move back and forth. And then at the end of this, we'll actually set up another variable and copy, like switch the arrays, and then have it go back through. So we'll say s is equal to x1, x1 is equal to x0, x0 is equal to s. And so now we just simple like swap of what they are. And so it should move back and forth. So it moves out. Nope. Oh, I didn't restart the timer. Amateur. Oh dear. Okay, let's try one more time. I think it's going to work. All right, so just a simple like application of linear interpolation. The fancy servos that go with robotic arms or CNC machines are programmable to move to specific locations, but they can also do so with specific velocities and acceleration curves. So doing this is like the simple, like we just need to slow this thing down and make sure it's usable for picking up the block and placing it without, even in the simulator, ramming it down on the table and causing the block to fly off, right? That's what happens in the physical lab too. So we can slow it down by using interpolation and interpolating through time, because we want to slowly move from one position to the next. We don't, at this point with what we're trying to do, we don't need to try to get into using like a specific spatial velocity or acceleration in there. But that's what a lot of work goes into for those companies selling the robotic arms or the high-end CNC machines, is how can we make sure that these are actually going to perhaps move this block at 0.1 meters per second from location A to location B, right? And when you're controlling 6, 8 motors at a time to do that and trying to keep this block moving at that certain space or certain speed, or with the CNC machine trying to move a very sharp tool through a piece of material at a very specific rate in keeping with a given profile to maintain accuracy, it can be a very challenging problem. But that's what a lot of that development and focus has been on, is trying to integrate that and use the ability of these devices to really kind of tackle complex engineering problems. That's why I like this one, because you actually get to like control the speed of it. And so if we wanted to, we could say, let's do something crazy and move it way too fast. So if we do that, you can see they can still move fast. But if you try to move servos with no feedback control on them too fast, if we made this something very small, it wouldn't even have the chance to move from one spot to the other. By the time you send one set of commands and it started moving there, it has already received another set of commands to move somewhere else. And so it like interrupts its motion and tries to do something else. And really the only time it ever gets to the correct spot is at the very end after the program is finished. So that's applying linear interpolation to controlling the speed of the servo arm. And hopefully this kind of tees you up for the lab challenge this week in capturing multiple data points and then programming the arm to repeatedly pick up and place that block. So that's all we got for this one. See you later.